In this chapter section, we will learn about the equilibrium that associate with solubility. We are going to also look at the equilibrium constant that associate with this, which is called solubility product constant. Please read the OER textbook for more details of chapter 16.2. In the previous chapter section, we already see that some ionic compounds can dissolve completely in water, and those ionic compounds would be called soluble ionic compounds. However, there are some of them that partially or not even dissolve in water, and those are what we call insoluble ionic compound. And what we are going to focus in this chapter section is that we are going to focus on how much of those insoluble ionic compound that can dissolve in water by looking at the solubility product constant, which is the equilibrium constant that tells us about the extent of how much the insoluble ionic compound can dissolve in the solvent, or in this case in water. For example, if you have the insoluble silver chloride ionic compound dissolved in water, is going to partially dissociate into silver ion and chloride ions. So in order to write the equilibrium constant expression or the solubility product constant, or K subscript SP, we can write this equilibrium constant as product, and we will exclude the reactant because the reactant is the solid. Therefore, KSP, or the solubility product constant, or the equilibrium constant for insoluble ionic compound, can be written include only the product in this case. And here is what KSP tells us, right? So KSP is when you have solid, when it dissolves in water, it's gonna partially dissociate, and how much of these available ions that dissociate in water, that's what we call the KSP. It tells us about the extent of how much is dissociated. Therefore, the KSP will tell us about the solubility of the ionic compound. For example, if the KSP is relatively large value, the ionic compound would be more soluble in that solvent. If you have KSP to be a relatively low value, that means that ionic compound will have less soluble. And the solution at equilibrium, where the maximum amount of solid can dissolve, we call this type of solution saturated solution. That means the KSP express the saturated solution at equilibrium. There are two units of concentration that we are going to use in this chapter section. One is grams per liter. This is express the gram solubility of the ionic compound. And another one is mole per liter, or molar solubility. This expresses the amount of solute ionic compound per liter of the solution. And the most common one that you will see often throughout this chapter would be molar solubility, or mole per liter. And the molar solubility or molarity, mole per liter, would be the one that we can use in the KSP calculation. Before we get into the calculation of solubility product constant, or KSP, let's take a look at how to write the equation and also write out the solubility product constant expression first. So let's take a look at example 1. Example 1 asks to write the dissociation equation and also to write the expression for the KSP. So let's take a look at example A. A given as magnesium hydroxide. If you look up the solubility rules, you will see that magnesium hydroxide is a solid. Therefore, the physical state would be S. The reason why it's solid because it's insoluble ionic compound. In order to write out the dissociation, so this one would be similar to the hydrolysis that we learned earlier in the salt chapter, which pretty much mean that you are going to dissociate or separate between cation and anion. In this case, you are going to end up with magnesium 2+ and 2 hydroxide ion in this case. Note that because some of magnesium hydroxide solid partially dissolve into magnesium ion and hydroxide ions, therefore the physical state of the ions have to be in aqueous. It indicates that some of these ions do dissolve in water, and some of these ions will be solvated or surrounded by water molecule. And because these salt is insoluble salt, or this ionic compound is insoluble. Therefore, this would be in equilibrium, which means that it will not dissociate completely. Therefore, you will need to use the reversible arrow in this case. Note that this is not the same as those ionic compounds that are soluble, such as sodium chloride. Sodium chloride is a salt that is completely dissociated in water because the sodium chloride is soluble ionic compound. Therefore, the physical state in water for sodium chloride would be aqueous, and this sodium chloride will hydrolyze or will completely dissociate into sodium ion and chloride ion. With note that just the one arrow that we use here, because this reaction is not reversible, because sodium chloride is going to completely dissociate into sodium ion and chloride ion, which is different from the magnesium hydroxide that is insoluble ionic compound. Therefore, in this case, because this magnesium hydroxide, when it's dissociate in water partially, is going to reach the maximum amount or reach the equilibrium. Therefore, in this case, to write out the KSP expression, it would be KSP equal to the concentration of the product. In this case, would be concentration of magnesium ion and hydroxide ion square. And we will exclude the reactant because the reactant for this process is solid. Again, for the equilibrium constant expression, we will include only aqueous and gas. The solid and liquid will be excluded. Now, I would like you to pause the video and complete example 1B and 1C. After you finish those two example problems, then resume the video again. For the ionic compound magnesium ammonium phosphate, when it's dissolved in water, is going to undergo the reversible reaction to produce magnesium 2 plus ion. And you also the compound also contain ammonium polyatomic ion, so you will need to also dissociate that into ammonium ions. And the last one would be the phosphate ion. Therefore, in this case, the KSP for this process would be KSP equal to the product magnesium ion multiplied by the concentration of ammonium ion and multiplied by the phosphate ion. Do the same thing for the next ionic compound. You will need to dissociate these ionic compound into their constitutive ions, which are 5 calcium ions plus 3 phosphate ions plus 1 hydroxide ions. And the KSP for this would be the concentration of the calcium ions multiplied by the concentration of phosphate ions and multiplied by concentration of hydroxide ions. And you will need to take the coefficient into account by raising them as the exponent. Next, let's take a look at example 2. Example 2 gives us the two values of the different ionic compound. One is with calcium carbonate, the other with lead carbonate. And it asks us to determine which salt or which ionic compound has higher molar solubility, which means which one is able to dissolve more in water. That's what it means. Molar, again, because molar solubility is in the unit of mole per liter. Therefore, it just asks us that in a liter of the solution, which one would be able to give or yield more mole of the solute ions in the solution. Now, if you look at the KSP value, as I mentioned before, that the KSP value tells us the extent of the solute, how much solute dissolve in the water. Therefore, in this case, if you compare between KSP of calcium carbonate and KSP of lead carbonate, we can see that KSP of calcium carbonate is higher than KSP of lead carbonate. Therefore, in this case, we can see that the higher value of KSP, the salt or the ionic compound would be able to dissolve more in the solution. So that means in this case, the answer would be calcium carbonate would have higher molar solubility or would be able to dissolve better in water than the lead carbonate. Next, we are going to take a look at the calculation of the KSP from the equilibrium concentration. Let's take a look at example 3. Example 3 gives us the information that in a saturated solution, the gram solubility of magnesium hydroxide in pure water is equal to these many grams per liter, and it asks us to calculate the solubility product for magnesium hydroxide. The solubility product is KSP, which means that this problem just asks us to calculate the equilibrium constant or the solubility product constant for the magnesium hydroxide. So that means in this case, before we start doing that, I'm going to go ahead, write out the KSP expression. In order to do that, I will need to first dissociate the ionic compound magnesium hydroxide into the ions, which is going to be magnesium ions plus 2 hydroxide ion in this case. Therefore, if you write the KSP for this dissociation would be the concentration of magnesium ions multiplied by the concentration of hydroxide ion square. Okay, so which means that if we know the concentration of magnesium and hydroxide ions at equilibrium, we should be able to plug them in to calculate for KSP. Now let's take a look at the next information that the problem given. The problem given that this solution is a saturated solution. Okay, recall from the previous slide, we already see that the saturated solution is the solution at equilibrium. So that means in this case, it already tells us that, hey, this is the solution at equilibrium, or it's the solution that has the maximum amount of solute that can dissolve in the solvent, right? So this is already at equilibrium. And it said that at this equilibrium or at a saturated solution, the concentration per liter is this many grams per mole. Note that the KSP expression have to be in unit of the concentration of molar per liter, right? So mole per liter or molarity in this case. Therefore, we will need to first convert this gram into mole per liter first. How can we do that? So pretty much we already learned how to convert from grams to mole by using the molar mass. We are going to do the same thing here. Add all of this up together to get its molar mass, and you are going to divide the grams by the molar mass to get mole. So that would be mole per liter. This value is the amount of mole of magnesium hydroxide that can dissolve in 1 liter of the solution at equilibrium. Therefore, at equilibrium, the concentration of magnesium would be the same as the concentration of magnesium hydroxide that we just calculated. The same thing for the hydroxide ion at equilibrium, the concentration would be 2 times of this that we calculate, because this is the concentration of magnesium hydroxide. Therefore, to take those into account and plug in all the value, you will get 1.30 times 10 to negative 4, which is the concentration of magnesium ions at equilibrium. And for hydroxide, it's going to be 2 times of that concentration raised to the power of 2. And you will get the KSP of 8.85 times 10 to negative 12. And KSP is an equilibrium constant, therefore there will be no unit. Next, I would like you to pause the video and complete example 4 and then resume the video again once you obtain your answer. Example 4 asks to calculate solubility product constant, which is KSP. Therefore, in this case, first we will need to write KSP expression to see what involved in the KSP expression. So I'm going to start with the ionic compound CaF2 calcium fluoride, and then we can dissociate this into calcium ion and fluoride ion. But they are subscript 2, so therefore you will need to add 2 in front of the fluoride ions. And the KSP expression for this would be only the product concentration, so it would be calcium ions multiplied by fluoride ions square. Because of the coefficient, that's why you need to raise to square. And to find out the concentration at equilibrium in order to plug into KSP, we need to look at the next given information. The next given information tell us that at the equilibrium, the concentration of the calcium ions is equal to this. And if you're looking at the problem, you will see that calcium ions is going to have 1/2 concentration of fluoride ion. Therefore, in order to find out the fluoride ions, you will just need to multiply the calcium ion 2 times to get into the concentration of fluoride ions. Then plug in all of this value, you will get 2.13 times 10 to negative 4, which is the concentration of calcium ion at equilibrium. Then multiply this concentration by the concentration of fluoride ions, which is 2 times of the concentration of calcium ion. Because if you're looking at the equation, you will see that the ratio between calcium and fluoride is 1-to-1 ratio. Then don't forget to square. And you will get the KSP equal to 3.87 times 10 to negative 11. Next, let's take a look at the determination of molar solubility from given KSP. For example 5 here. Example 5 asks us to calculate both molar solubility, which is going to give us in unit of mole per liter, and gram solubility, which is going to give us in the unit of grams per liter. Okay, of calcium carbonate at 25 degrees Celsius when calcium carbonate dissolved in pure water to make saturated solution. Again, the keyword for saturated solution is that it tells us that this is going to be at equilibrium, which means that we are going to look at the equilibrium constant to help us determine the molar concentration at equilibrium. Okay, so in this case, first step is to write out the dissociation of calcium carbonate. Okay, so you are going to get calcium ion plus carbonate ion. And because this is involved with the equilibrium, therefore we are going to use Rice table or ICE. Okay, because E stands for at equilibrium, the unit for Rice table must be in the unit of mole per liter or molarity. So this problem is similar to the equilibrium problem that we see many times now. Pretty much it's just tell you to find out what is the equilibrium concentration of these two products. That's all it asks you to find. So in this case, to fill out the Rice table, you will need to first consider each of these species. We know that calcium carbonate solid will not be part of the equilibrium expression, therefore we can ignore this. And if you look at calcium ions and carbonate ion, before calcium carbonate dissolve in water, the amount of calcium and carbonate would be 0 molar because it has not dissolved and has not dissociated into ions yet. For the change, we don't know how much, but these two are the product, therefore the change will be plus X. And at equilibrium, both of these will be X. Therefore, if you write out KSP expression for these, you are going to get KSP equal to concentration of the calcium ion multiplied by carbonate ion. And if you plug in the value of KSP, which is given to us, which is 4.5 times 10 to negative 9, and plug in the concentration of calcium ion and carbonate ion at the equilibrium point, you're going to get X times X, which is going to give you equal to X squared. In order to get X, you are going to do the square root of these two. And the value of X will equal to 6.71 times 10 to negative 5. This calculation should contain two significant figures at the end, and X is equal to the concentration of calcium ions and carbonate ions at equilibrium. Therefore, the concentration of calcium ions at equilibrium would be the same as concentration of carbonate ion at equilibrium, which is equal to 6.7 times 10 to negative 5 molar. Now, if you look at the reaction, you can see that for calcium ions and carbonate ions to be produced equal to 6.7 times 10 to negative 5 molar, the amount of calcium carbonate of the solid have to be dissociated at the same amount because the reaction is 1 to 1 to 1 mole ratio. Therefore, in this case, we can also say that the amount of calcium carbonate that dissolve in water would also be 6.7 times 10 to the negative 5 as well. So this would be also the concentration of calcium carbonate that can dissolve, or this is what we call molar solubility of calcium carbonate. So to answer the first question is molar solubility, we can say that the molar solubility of calcium ions at equilibrium would equal to concentration of carbonate ion at equilibrium. It also will equal to the amount of calcium carbonate that can dissolve, which is equal to 6.7 times 10 to the negative 5 molar. Next, we will need to calculate grams per liter or grams of solubility. To do this, you will need to use molar mass of calcium carbonate in order to convert from mole to grams and to obtain the grams of solubility. So the setup for this would be 6.7 times 10 to negative 5 mole per liter, which is the molar solubility that we just calculated, and then multiply this by the molar mass of calcium carbonate, which is 1 mole equal to 100.087 grams of the calcium carbonate. And you will get the gram solubility equal to 6.7 times 10 to negative 3 grams per liter. And this answer right here would be the gram solubility of the calcium carbonate. And this answer here would be the molar solubility of the calcium carbonate. These two numbers tell us that, the first one is tell us that for every 1 liter of the solution, calcium carbonate can dissolve only 6.7 times 10 to negative 5 mole. Or from the gram solubility, you can say that for 1 liter of the solution, only 6.7 times 10 to negative 3 grams of calcium carbonate that can dissolve in water. I would like you to pause the video and complete example 6 and resume the video again once you complete it. Example 6 asks to calculate molar solubility of silver carbonate and the concentration of silver ions and carbonate ions at equilibrium. And note that the molar solubility is the mole per liter. It tells us how much or how many mole of silver carbonate can dissolve in 1 liter. Therefore, this amount or this concentration would be the concentration at equilibrium. The problem gives us the insoluble ionic compound with the KSP or the equilibrium constant or the solubility product constant. Therefore, you will need to set up Rice table to find out the concentration at equilibrium. For the reaction for the Rice table, you will start with the insoluble ionic compound, dissociate into their ions. Because silver carbonate is insoluble ionic compound which is in solid state, therefore we will not include this in the equilibrium constant expression or KSP. At the beginning, before silver carbonate dissolve in water, there should be no concentration of the silver ions and carbonate ions. And for the change, you will see that the stoichiometric ratio between silver carbonate, silver ions, and carbonate ion is 1 to 2 to 1 ratio. Therefore, the change for silver ion would be plus 2x because over time product would increase, and for carbonate ion will be plus x because over time the product also increase as well. And the concentration of silver ion would be 2 times greater than the carbonate ion according to the stoichiometric ratio. Therefore, the concentration at equilibrium for silver ions and carbonate ion would be 2x and x respectively. Next, write KSP expression in order to solve for x. KSP for this reaction would be silver, and we have the coefficient 2 in front of it. So silver ion would be silver ion squared multiplied by the concentration of carbonate ion. Then plug in the value of the KSP that's given. And note that at the equilibrium, the concentration of the silver ion is 2x, but this 2x is the concentration of silver ion at equilibrium, and we also need to raise by the power of 2 as well. And the concentration of carbonate is x at equilibrium, so we just add x to it. And so for this, you will get 8.1 times 10 to the negative 12 equal to 2 squared, which is equal to 4, and then x squared multiplied by x would equal to x cubed. Then divide both sides by 4 and you will get 2.025 times 10 to negative 12 equal to x cubed. And to get rid of cube, you are going to need to do cube root on both sides. And you will get x equal to 1.3 times 10 to negative 4. This value of x represent the molar solubility of silver carbonate. It tells us that the silver carbonate can, in 1 liter, it can dissolve 1.3 times 10 to negative 4 mole at equilibrium, and this 1.3 times 10 to negative 4 mole then will dissociate into 2 silver ions and 1 carbonate ion. Therefore, the concentration of the carbonate ion would be the same as the concentration of the silver carbonate that can dissolve in water. And the concentration of the silver ion would be 2 times x, which means it's going to be 2 times of the concentration of these two. Don't forget to include the unit for the concentration. To summarize, the molar solubility pretty much it just tells us that what is the concentration at equilibrium. So for example, example 6, right, asking for molar solubility of silver carbonate. Pretty much it asks us to find out how much this silver carbonate can dissolve in water at equilibrium. And because the ratio from the silver carbonate and silver ion and carbonate ion is 1 to 2 to 1 ratio, therefore the molar solubility of the silver carbonate would be the same as the x value because it's the 1 to 1 ratio. And if you want to look at this, go back to example 5, you will see the same thing. The molar solubility pretty much represent the x value at equilibrium. Same thing for example 6 as well. The molar solubility would represent the x value at equilibrium. And the concentration of each ions at equilibrium, that is going to depend on the ratio that each of these salt would giving off. To master in this concept, you will need to complete the DIY problem on page 69. The answer keys will be posted on Moodle. Next, we are going to learn how to use the reaction quotient Q and the equilibrium constant KSP to help us predict the precipitation. You learned about these two Q and K before in Chem 122. The reaction quotient Q represents the reaction at any point. However, the equilibrium constant K represents the point at equilibrium. So by comparing Q and K value together, we will be able to predict the direction of the reaction, whether it's going to shift toward the product or toward the reactant, or is already at equilibrium. For example, if the value of the reaction quotient is less than the K value or the equilibrium constant value, it tells us that this at this point is not at equilibrium yet. At this point, we have less product than the reactant. Therefore, the reaction will proceed toward the product to make more of the product until it's reached the equilibrium. At this point, if we talk about the solution or solubility equilibrium, this point will represent the unsaturated solution, which means that you have water or solvent and you can add more of the ionic compound to it, and it's not going to reach the saturated point yet. It's called unsaturated. That means it can dissolve more and there will be no precipitate observed. For example, if you have ammonium acetate ionic compound that can dissolve in water to dissociate into ammonium ion and acetate ion, the point when you dissolve this ionic compound into water and this ionic compound still be able to dissolve, at this point we call it unsaturated solution, and at this point is when Q less than K. We will not observe solid left, or we will not observe precipitate. Next, if Q equal to K, is represent that that solution is already at equilibrium, which means that that solution is the saturated solution. This solution is when the maximum amount of solute can dissolve in the solvent. Now, if you look at this figure here, from unsaturated solution, if you continue adding more of the ionic compound until it cannot dissolve anymore, at this point is what represents equilibrium point, and this solution would be called saturated solution. At this point is when Q equal to K. You will see that the maximum amount of ions will represent at this point. You will also observe some of the solids that cannot dissolve as well, that are in equilibrium with all of these ions. When Q is greater than K, this solution is not at equilibrium. At this point, there are more product than the reactant. Therefore, the reaction will shift toward making more of the reactant until it's reached equilibrium. And at this point, when Q greater than K, we call it supersaturated solution. This is when the precipitate would form. Because it's beyond the point that the solute can dissolve in the solvent, or it's beyond the maximum amount that the solute can dissolve in the solvent. The supersaturated solution can be achieved by heating the saturated solution until all of these leftover solid in the saturated solution dissolve. At this point, the solution at higher temperature, it will become unsaturated again, which means that it can dissolve all of these solid at a higher temperature. We learned in Chem 122 before that the solubility of the ionic compound will increase as temperature increase. Similar to if you want to dissolve salt, in order to dissolve more, you just have to heat it up and then you will be able to dissolve more. So this is going to be the same idea here. Next, cool this solution down slowly until it reaches the original temperature and do not disturb it. At this point, without disturbing, you will see that at this point, the solution will be able to dissolve all the solid. At this point, we call it supersaturated solution. We call this point supersaturated solution because it's beyond the maximum amount of solute that can dissolve in the solvent. How do I know? Well, if you compare between these two flasks right here, these two have the same temperature. The saturated solution will have some of the solid left. However, at the same temperature, you will see that this one of those solid has been dissolved already and is still dissolved in this solution. Therefore, this solution is going to be supersaturated solution because it contains beyond the maximum amount of solute that can dissolve in the solvent. And for the supersaturated solution, the Q will be greater than K. And if you disturb this supersaturated solution, the precipitate would form in order to reach or establish the new equilibrium again. There are several ways to disturb the supersaturated solution, but one of the common way is to do seeding by adding just tiny amount of the solute in this supersaturated solution in order to initiate the precipitation. And if you do that, you will see that once this supersaturated solution is disturbed, it's going to precipitate out the solid in order to reach the new equilibrium again or reach the saturated solution again. In summary, to predict the precipitation, you will need to compare the Q and the K value. If the Q less than K, which means that you can add more solute into the solvent, the solution is at unsaturated solution, is not at equilibrium yet. If Q equal to K, this at this point is already at equilibrium. The solution is called saturated solution. You are going to have the amount of solid in equilibrium with its ions. And for the supersaturated solution, the Q will be greater than K, and at this point, the precipitate would form in order to reach the new equilibrium again. Now let's take a look at example 7 that will use the idea of predicting precipitation by using the reaction coefficient and the equilibrium constant KSP. Example 7 give us information and ask, will a precipitate form? In this case, you will need to compare the value of the Q versus the K. You need to see whether at this point it's already at equilibrium or at this point it's not at equilibrium yet and which direction it's going to shift. So I'm going to go ahead set up the Q value in this case. So the Q expression for this reaction would be the same as how to write the K expression. You are going to include those species that are in aqueous and gaseous form but exclude the solid and liquid. Therefore, I'm going to include magnesium ion concentration and fluoride ion concentration and squared because we have coefficient 2 in front of the fluoride ions. So that means if we know concentration of each of these species, then we should be able to find out the Q. The problem gives us the magnesium concentration, which is 0.0025. So I'm going to plug in the value for that. Going to plug in the value of magnesium concentration, which is 0.0025 molar. Now, the problem doesn't give us the concentration of fluoride, but we know that the concentration of the fluoride would be 2 times of the magnesium. In this case, I'm going to go ahead multiply the concentration of magnesium ion by 2 because fluoride ion have 2 times higher concentration than magnesium. And then don't forget to square the concentration of the fluoride. You are going to obtain the answer equal to 6.3 times 10 to negative 8. Now if you compare between the Q that we calculated and the K value that is given, we see that the Q is greater than K. Therefore, this at this point is tell us that it's not at equilibrium yet, and at this point is going to be the supersaturated point because you are having more of the product than the reactant. Therefore, in this case, the precipitate would form. Next, let's take a look at more challenging example. Example 8 give us the information of potassium iodide and lead nitrate. However, it gives us the KSP of something else, which is lead iodide. So in this case, it's asking us whether the precipitate would form or not. So this is when we will need to also compare between Q versus K. The problem gives us 3 species. One is potassium iodide, the other is lead nitrate, and the last one is lead iodide. So which Q and K that we are going to compare then? We are going to look at the lead iodide in this case because the KSP that is given is belong to lead iodide. And if you use the solubility rules to predict the solubility of lead iodide, you will see that lead iodide is an insoluble ionic compound, which means that the physical state of lead iodide would be solid. And the KSP expression of lead iodide can be written from the dissolution of lead iodide. Same for the expression for the reaction coefficient as well. It would be the concentration of the lead times the concentration of iodide square. In order to compare the value of the Q and the K, we will need to find out the given concentration of the lead ions and iodide ions first in order to plug into the Q expression and obtain the value, so that way we can compare these two values to predict whether the precipitate would form or not. The problem gives us the information about potassium iodide and lead nitrate. If you use the solubility rules, you will see that the ionic compound that contain the group 1 metal ions would be soluble ionic compound. Therefore, potassium iodide would be soluble, which means that it's going to completely dissociate into cation and anion. Same thing for lead nitrate as well. The ionic compound that contain the nitrate ions would be soluble ionic compound. Therefore, the lead nitrate would be a soluble ionic compound, which means that it's going to completely dissociate. And if you look at the dissolution of potassium iodide and lead nitrate, you will see that these two equations contain the iodide ions and lead ions that eventually will allow us to use as a concentration to plug into the Q expression. First, let's take a look at the given volume and the concentration of potassium iodide. From the given volume, convert this into liter and multiply by the concentration. You are going to obtain the number of mole of potassium iodide equal to 0.0010 mole of potassium iodide, which means that if you have 0.001 mole of potassium iodide, and because potassium iodide is a soluble salt or soluble ionic compound, therefore it's going to dissociate 100%, which is going to give us the same amount of mole for potassium ion and the same amount of mole for iodide ion. Next, do the same thing with the lead nitrate. Use the volume 80 milliliter, convert that into liter, and then multiply by its concentration. You are going to obtain the number of mole of lead nitrate equal to 0.04 mole of lead nitrate. And again, lead nitrate is an soluble ionic compound, therefore it's going to dissociate 100% to give off the same amount of mole of the lead ion, and it would be 2 times of the concentration for the nitrate ion. So the nitrate ion would be 0.080 mole. Note that we cannot use this mole and plug into the Q expression, because according to the Q expression, we need it into the concentration. So how can we convert into concentration? If you look at this, it said that when potassium iodide is added to lead nitrate, which means that when potassium iodide that have 20 milliliter add to the 80 milliliter of lead nitrate, the total volume now going to become 20 plus 80, which is going to be 100 milliliter. Therefore, in this case, this amount of mole of iodide would be present in the 100 milliliter total volume of the solution. Same thing for the lead ion as well. Therefore, we will need to convert this number of mole into the concentration by dividing with the total volume, and you will get the concentration of iodide ion equal to 0.01 molar. Next, do the same thing for the lead ion, find its concentration. The concentration of the lead ions would be the number of mole of lead divided by the total volume. In this case would be 100 milliliter. Convert that into liter. You are going to get 0.10 liter. Therefore, the concentration of lead ion would equal to 0.4 molar. Now we know the concentration for both iodide ion after it's mixed, and also the concentration of lead ions after it's mixed. Therefore, we can use these two concentrations to plug into the Q expression now. And the value of Q will equal to 4.0 times 10 to negative 5. Next, compare the Q and K value. In this case, the value of Q is greater than K. It's determined that this solution is going to be a supersaturated solution, and therefore the precipitate would form. Next, let's take a look at example 9. If a solution contains 0.002 mole of chromate ion per liter, what concentration of silver ion must be reached by adding solid silver nitrate before silver chromate begins to precipitate? Neglect any increase in volume upon adding the solid silver nitrate, and is given the KSP of the silver chromate equal to 9.0 times 10 to negative 12. Again, the keyword for this is precipitate would form, right? Another one is KSP of that. Therefore, in this case, we are going to look at the ionic compound that belong to KSP, and we are going to write the dissociation of that. So I'm going to go ahead write the dissociation of the silver chromate, because the KSP given is of this species. So I'm going to write out this silver chromate dissociation into 2 silver ions and chromate ion. The problem asks how much silver ion need to be added before the silver chromate begin to precipitate. So we will need to understand the relationship between Q and K first. When Q less than K, this solution is unsaturated solution, which means that you can dissolve more of the solute into the solution. If Q equal to K, this solution is already at equilibrium. And when Q is greater than K, this is when the precipitate would form. So that means when it asks for how much it add before it begin to precipitate, therefore we will need to know at least the concentration at equilibrium, because beyond equilibrium point, that's when the precipitate will begin to form. So that means in this case we need to find out Q that is equal to K. And if you look at the KSP value, the KSP value is 9 times 10 to negative 12. Therefore, in this case, we are going to set the Q, which is equal to K, which is going to equal to 9 times 10 to negative 12. Next, we are going to set up the Q expression and find out the silver ion concentration. Plug in the Q value and also plug in the concentration of the chromate ion, then solve for the concentration of silver ion. Note that this 0.002 mole is per liter, therefore this number is the molarity concentration. You will get the concentration of silver square equal to 4.5 times 10 to negative 9. Square root both sides, you are going to get the concentration of silver ion equal to 6.7 times 10 to negative 5 molar. Therefore, in order to make the solution of silver chromate to precipitate, we will need to add the concentration of silver ions to be at least 6.7 times 10 to negative 5 molar. And we can add these silver ions by adding the solid silver nitrate, because silver nitrate is a soluble ionic compound because it contains nitrate ion. Therefore, this ionic compound will completely dissociate to give off silver ions and nitrate ions. So by adding the silver nitrate, it's going to yield the silver ion. And when you add this silver ion in the solution, at least this amount, the solution will start to begin to precipitate. Now let's consider example 8 and example 9 again. When you look at example 8, you can see that potassium iodide contains the iodide ions that is in common with the iodide ions in the lead iodide. Same thing for the lead nitrate. Lead nitrate contains lead ions that is in common with the lead iodide. Therefore, in this case, whenever that you see the species that are present in the two substances that are in common, we call these the common ions. Same thing for example 9 as well. The silver ion that present in the silver chromate is the same as the silver that present in the silver nitrate. Therefore, in this case, the silver nitrate and silver chromate has the same common ion, which is the silver ions. We already see the example of common ions in the previous example 8 and 9. So here we're going to look into more detail of the effect of the common ions. Again, the common ion is an ion or cation that is in common between the two substances. And the common ion effect, it will affect the equilibrium according to the Le Chatelier principle. We are going to see how the reaction would shift when the common ion is present in the reaction. Before we begin the calculation involve the common ion, I would like you to go to page 68, example 5, to obtain the molar solubility of calcium carbonate in pure water at 25 degrees Celsius. Page 68 can be found on the third slide of this video. And the value of the molar solubility of calcium carbonate in pure water at 25 degrees Celsius is 6.7 times 10 to negative 5 molar. To obtain this value, please refer to page 68, example 5. We already discussed how to calculate for molar solubility of calcium carbonate on this page here. One thing I would like to point out is that this molar solubility of calcium carbonate is in pure water. Okay, so let's highlight that. In pure water, without anything else, you can, in 1 liter of that pure water, you can dissolve 6.7 times 10 to negative 5 mole of calcium carbonate. That's what the molar solubility means. Now let's take a look at example 10. Example 10 asks to calculate molar solubility of calcium carbonate also, but in the solution that contain this molar of calcium nitrate. So I'm going to go ahead, write out the chemical formula of calcium nitrate. Calcium nitrate is CaNO3 parenthesis 2. Calcium nitrate, if you look up the solubility rules, you will see that calcium nitrate is a soluble ionic compound. So I'm going to write the physical state as AQ, which means that when calcium nitrate dissolved in water, it's going to be an aqueous solution that will dissociate completely to give the calcium ions and 2 nitrate ion. So that means if you look at the stoichiometric ratio here, you can see that every 1 mole of calcium nitrate would give off 1 mole of calcium ion and would give off 2 mole of nitrate ion. Therefore, if you're looking at the concentration of calcium nitrate, assume that this is in 1 liter, you can say that in 1 liter, there would be 0.01 mole or molar of calcium nitrate, which is going to dissociate completely to give off the same amount of mole or concentration of the calcium ions, and it would be 2 times concentration of the nitrate ion because of the coefficient of the nitrate is 2 times higher than the calcium ions. So now if you consider the molar solubility is asking for molar solubility of calcium carbonate. So I'm going to write out calcium carbonate. Calcium carbonate, if you look up the solubility rules, you will see that calcium carbonate is insoluble ionic compound. Therefore, the initial state would be solid. And this solid, when it dissolves, is going to dissolve in a small amount that will eventually reach equilibrium to give off calcium ions and carbonate ion. You probably recognize that if you compare between calcium nitrate equation and calcium carbonate equation, these two equations contain calcium ions. Therefore, in this case, the calcium ion is considered to be a common ion. So in this case, calcium ion would be common ion. Why the common ion is significant? Well, the common ion will play a role when we calculate for the molar solubilities. Again, because molar solubility that we want to calculate is of the calcium carbonate. Therefore, in this case, this reaction is in equilibrium. So we need to set up Rice table to find out the concentration at equilibrium or how much it can dissolve at equilibrium. So I'm going to set up Rice table. And again, the unit of Rice table is molar or mole per liter. So for the solid, we will ignore it because it's not part of the equilibrium constant expression. And initial, normally you will need to add initial concentration of calcium 2 plus equal to 0. However, this calcium carbonate is dissolved in the solution that contain calcium nitrate, which means that it has the common ion present already in the solution. Therefore, the initial concentration of calcium ion would be 0.01 mole per liter. And because there is no common ion for carbonate ion, therefore the concentration of the carbonate would be 0 molar. Again, I would like to draw the picture so that way you understand a little bit better here. So let's take a look at the flask or the beaker. Okay, so this beaker contains a solution. And this solution contains calcium nitrate, right? So that means there should be calcium floating around. There should be nitrate floating around according to the first equation that we write out. Okay, so let me rewrite that better. So next, when you add calcium carbonate into this solution, you will see that both calcium ions are present. So this is the initial concentration of calcium ions. So that's why we will need to take that into account, right? Because initially there is a concentration of the calcium ions, but initially there is no carbonate that present in the solution. Therefore, the change for this would be positive X for calcium and then positive X for carbonate. And at equilibrium, concentration of calcium ion would be 0.01 plus X, and then for carbonate would be X. And again, all of these have to be in the unit of molarity. Next, to find out the X or the molar solubility, you will need to use KSP to set this up. So we will use KSP, which is equal to concentration of calcium ions multiplied by the carbonate ion, and plug in the value of given KSP, which is 4.5 times 10 to negative 9, equal to the concentration of calcium ion, which is 0.010 plus X, and then for the carbonate would be X. Now, if you start to distribute this X into these parentheses, you are going to end up getting 0.01X plus X squared. This one you are having both X squared and X, which you are going to need to use quadratic equation to help determine the X is too complicated. So we are going to simplify this. We are going to ignore the X that come with 0.01 because the change of X is insignificant. Compared to the original concentration, right? So the one that is undergo change is not much compared to the original concentration. Therefore, we can we can ignore this plus x compared to the original concentration. So now rewrite the equation again. You are going to get 4.5 times 10 to negative 9 equal to 0.010 times x, right? Because this multiplied by x, so that's why you're gonna get that minus times x, and divide both sides by 0.01. You're gonna get x equal to 4.5 times 10 to negative 7, which is equal to x. This x is what is called molar solubility, which represents the concentration of the carbonate ion at equilibrium. It represents the change or how much calcium carbonate can dissolve, right, until it's reached equilibrium. And with this molar solubility of calcium carbonate, we can say that in 1 liter of the solution that contain 0.01 molar of calcium nitrate, which contain the common ion calcium, the calcium carbonate can dissolve 4.5 times 10 to negative 7 mole. That's what it means. Next, let's compare the molar solubility of calcium carbonate in pure water versus the molar solubility of calcium carbonate in common ion solution. You can see that the calcium carbonate can dissolve more in pure water than in the common ion solution. And we can conclude that the common ions suppress the ionization of the ionic compound, causing the ionic compound to dissolve less than it normally would in pure water. The common ion effect relies on the Le Chatelier principle, because if you think about it, if this reaction is at equilibrium, when you disturb the equilibrium by adding more of the product, the reaction will shift toward the reactant. Therefore, in this case, the solid will not be able to dissolve much at all. It's going to dissolve less because these ions that present in the solution would cause the reaction to shift toward the reactant. Therefore, the solubility of the solid will decrease. And for pure water, in the absence of the common ion effect, the reaction is not at the equilibrium yet. Therefore, the calcium carbonate would be able to dissolve more in order to establish the equilibrium by producing the calcium and carbonate ion. Next example, 11. Calculate molar solubility of silver carbonate in 0.05 potassium carbonate solution. Again, it's giving us two different types of the substance. We have silver carbonate and we have potassium carbonate. You probably recognize that the carbonate and carbonate are the same. Therefore, this type problem is the common ion effect problem again. So I'm going to write out the chemical formula of potassium carbonate. Would be KCO3, and because carbonate is 2 minus, therefore we need 2 potassium to balance the charge of the carbonate. And if you look at this problem, it asks us to calculate molar solubility of silver carbonate. Therefore, in this case, we know that silver carbonate would be the one that we will need to set up the Rice table of, because we need to find out the X at equilibrium. And what is the identity of the potassium carbonate then? If you look up potassium carbonate solubility from the solubility rules, you will see that potassium carbonate is going to be soluble salt. So we're going to start with aqueous. This salt will completely dissociate, giving off 2 potassium ions and 1 carbonate ion, which means that if you start with 0.05 molar of potassium carbonate, you are going to end up with 0.10 molar of potassium ion and 0.050 molar of carbonate ion. And again, as I mentioned earlier, these two species contain carbonate. Silver carbonate contains carbonate and potassium carbonate also contain carbonate. In this case, the carbonate ion is the common ion. We will need to consider this common ion when we start the initial concentration, when we set up the Rice table. So next step would be set up Rice table, because we want to find out the equilibrium concentration, which represent the molar solubility of silver carbonate. So we are going to set up Rice table of silver carbonate because ask of the silver carbonate. Silver carbonate, if you look up the solubility rules, you will see that silver carbonate is going to be insoluble ionic compound. Therefore, the physical state would be solid. And this solid would slightly dissociate into its ion. So 2 silver ion plus carbonate ion. Again, because this is insoluble ionic compound, therefore we are going to partially dissociate. That's why we are going to use the reversible arrow. The first one is soluble ionic compound. It's going to fully dissociate. That's why I use only one head arrow, on one direction arrow. Now, filled out the rice table, we will ignore the solid because not part of the equilibrium constant expression. And for the silver ion concentration, there is no common ion for silver, so this would be 0 at the beginning. And we see that the carbonate, there is the common ion for carbonate. And this silver carbonate is dissolved in potassium carbonate ion solution, which means that if you have a beaker that contain a solution of potassium carbonate, this potassium carbonate would dissociate into 2 potassium and carbonate ion. So that means at the beginning, before you add any silver carbonate to this solution, you already have the carbonate present in the solution. Therefore, the initial concentration of the silver carbonate, the initial concentration of the carbonate would be the same as what present before we add the silver carbonate. And now this represents when we add silver carbonate to it. Right, so that means we will need to add the initial concentration of carbonate, which is going to equal to 0.050 molar. Okay, so again, it's come from the common ion. It's come from the fact that at the beginning, before we add silver carbonate, the carbonate ions is already present in the solution from the potassium carbonate. Okay, now the change for silver ion would be plus 2x because it's the stoichiometric of 2, right, per 1 ratio. So carbonate would be plus x. And at equilibrium, the silver ion would be 2x and the carbonate ion would be 0.050 plus x molar. So for x, x would represent the molar solubility of silver carbonate. So we are going to solve for x by using KSP. The KSP expression for this would be silver ion square multiplied by carbonate ion. Plug in the value of KSP, which is 8.1 times 10 to negative 12, equal to concentration of silver at equilibrium is 2x, and this concentration at equilibrium is square, so you don't forget the square. And you are going to multiply by the concentration of carbonate ion, which is 0.050 plus x. Again, if you are distribute all of this into the parentheses, you will eventually need to use quadratic equation to help you solve for x. Therefore, in this case, I'm going to ignore the plus x because the plus x is insignificant compared to 0.05 compared to the initial concentration. And the reason for that is because potassium ion is completely dissociated. So this is come from everything that potassium carbonate has, right, dissociates into this. But for this carbonate in silver carbonate is only partially dissociated. So that means in comparison, the X that is dissociated would be a lot less than 0.05 because you compare between insoluble salt versus soluble salt. Therefore, the plus X would be insignificant compared to 0.05. Then you will need to solve for X, and you get X equal to 6.4 times 10 to negative 6. And this X represents molar solubility of silver carbonate in 0.05 molar potassium carbonate solution. Next, take a look at the conceptual problem on example 12. In which of the following would silver chloride be most soluble? And it says so-called ordered apply. So I'm going to go ahead write out the chemical formula of silver chloride. Silver chloride is AgCl. It's asking for if this silver chloride solid dissolve in a solution, which one would be able to allow silver chloride to dissolve the most. And as we learn from the common ion effect, the common ion effect will suppress solubility of the ionic compound. Therefore, in this case, if the solution doesn't have any common ion effect, that solution would be able to dissolve the ionic compound the most. So I'm going to go ahead look at choice A. Choice A said that if we dissolve this ionic compound in pure water. And again, pure water doesn't contain common ion effect. Therefore, in this case, pure water would be one of the choice answer that silver chloride would be able to dissolve in the most. Now let's take a look at choice B. Choice B contains chloride ions, that is the common ion with the silver chloride ion. Okay, so this chloride is the common ion. And the common ion chloride will suppress the solubility of silver chloride. So that means choice B is incorrect. Now let's take a look at choice C. Choice C contains silver nitrate. And again, the silver is the common ion in this case. Therefore, the common ion silver will suppress the solubility of silver chloride. Therefore, silver chloride would not be able to dissolve well in silver nitrate. So choice C would be incorrect. Now let's take a look at choice D. Choice D doesn't contain any common ion that's similar to the silver chloride. Therefore, in this case, there is no common ion effect. So choice D would be another choice that silver chloride would be able to dissolve in the most. Example 13. What is the effect on the amount of solid lead bromide and the concentration of lead ion and bromide ion when each of the following are added to a saturated solution of lead bromide? So I'm going to go ahead write out the lead bromide equation. So lead bromide is insoluble ionic compound according to the solubility rules. Therefore, lead bromide would dissociate into lead ion partially, and I forgot subscript 2, and 2 bromide ions partially. Okay, so this is the saturated solution. Okay, so that's what the problem giving us, which means that this solution is at equilibrium. So that means if you are disturbing by adding any of these, it might disturb this equilibrium. Therefore, the reaction would either shift to the right or shift to the left in order to establish the new equilibrium again. So we're going to go ahead look at each of these actions. So let's take a look at action A. Action A is adding lead acetate. If you look at the solubility rules for lead acetate is soluble ionic compound. So I'm going to write this as AQ. Therefore, when lead acetate dissolved in water, is going to give off lead ion and 2 acetate ion. And you probably recognize this, that the lead ion is the common ion with the lead bromide ion, right? So this is the common ion because it contains lead. So lead acetate contains common ion lead with the lead bromide. Therefore, in this case, when you add the concentration of the lead acetate, the concentration of this lead ion would increase. And because the concentration of lead ion increase, therefore it disturbs the equilibrium. The reaction is not at equilibrium anymore. The reaction would shift according to the Le Chatelier principle to minimize this by shifting toward the reactant. Therefore, in order for this to shift, or in order for the lead ion to convert to lead bromide, it needs to react with the bromide ion. Therefore, when you add the lead acetate, the concentration of the lead ion would increase, but the concentration of the bromide ion will decrease because it needs to react with the lead ion, and it's going to shift to produce more of the lead bromide. Next, the B action. B action is adding potassium bromide into the equilibrium solution of the lead bromide saturated solution. Potassium bromide is soluble ionic compound, so it would be AQ. When it dissolves in water, it's going to completely dissociate into potassium ion and bromide ion. Again, in this case, we notice that the bromide ion is the common ion that we found between the potassium bromide and lead bromide. Therefore, in this case, by adding potassium bromide, we are adding the bromide concentration. Therefore, the bromide concentration will increase. And because concentration of bromide increase is disturbed the equilibrium, the reaction would need to shift in order to produce more of the reactant by reacting with the available lead ions. Therefore, the concentration of lead ion will decrease as it reacts with the added bromide ion, and the concentration or the amount of solid of lead bromide will increase because these two will eventually shift to form more of the precipitate. Next, action C is adding lead bromide into the lead bromide saturated solution. Lead bromide, if you look up the solubility rules, you will see that lead bromide is going to be insoluble ionic compound or solid. This lead bromide is the same as the lead bromide solution. Therefore, by adding more of the solid, the amount of the solid will increase. However, the amount of the ions will stay the same. The reason for that is because this solution is already at the equilibrium. The amount of lead bromide will not be able to dissolve anymore. Therefore, this concentration of the ions is already at equilibrium. It will not be able to dissociate more to produce more of the ions. In this case, the only thing that will increase would be just the amount of the solid, but the amount of the concentration of the ions will stay the same. This topic is one of the challenging topics you will need to practice more by doing the DIY problem on page 74. The answer key for this will be posted on Moodle. And again, if you have any question, please do not hesitate to email me.